In the 21st podcast, we're going to be looking at air resistance and terminal speed and how forces affect these things. In class, we've been doing a lab on how the number of coffee filters affects the coffee filter's terminal speed, or effectively how the mass of something affects its terminal speed as it falls. So terminal speed is the fastest speed achieved by something moving through air or fluid, and in the case of a falling object, it's the fastest speed that it achieves. So these diagrams show the coffee filter after 1 second, 2 seconds, and 3 seconds. The down arrow, the red arrow, shows the weight of the coffee filter, and we can see that that's constant, it doesn't change. The green arrow represents the air resistance that the coffee filter experiences. We can see that after 1 second, because it's only moving slowly, the air resistance is quite small. After 2 seconds, it's traveling faster, so the air resistance is bigger, but still not as big as the weight. After 3 seconds, though, the air resistance has reached its maximum value and is equal to the weight. And at this position, we have reached terminal speed. The blue arrow represents the resultant force, or the two forces here added together. We can see that resultant force here is quite big, so the object is still accelerating, according to Newton's second law. In this situation here, the resultant force is much smaller. The red one plus the green one, obviously they're in opposite directions, gives only this value. So the resultant force is much smaller and it's not accelerating so quickly. Here, the resultant force is almost zero because the two forces are about equal now, and the object stops accelerating. If we were to look at a speed time graph of an object falling through air, it would look something like this. Initially, the object is accelerating, and that's shown by this section of the graph. The graph is increasing at a steady rate, so the speed is changing with time, which is an acceleration. But we can see that the slope gradually gets less and less. The slope is reducing, and eventually the slope actually is zero. The slope here is zero. The slope is the change in speed over time, which is actually the acceleration. So here we have no acceleration. We've reached terminal speed. The object is not speeding up or slowing down. Now we know the terminal speed of a coffee filter is around about 1 meter per second as it falls through the air, but let's have a look at some other objects' terminal speed. A belly down skydiver. Normal position for a skydiver, arms out. Terminal speed is around 200 kilometers per hour. A peregrine falcon, a bird, in an attack stoop, so happens to have the same terminal speed as a bullet falling back to Earth. If a bullet was shot up into the air, it would fall back to Earth at 320 kilometers per hour, same as a stooping peregrine. And a head-down skydiver. A head-down skydiver, the world record speed achieved 988 kilometers per hour. This was achieved in very thin atmosphere at fairly high altitude to reduce the air resistance even more. So what factors affect the terminal speed of a falling object? Well, we know that mass. Our class lab, our in-class lab on coffee filters showed that the relationship between the terminal speed and the mass is approximately this. Terminal speed is proportional to the square root of mass. But what other factors affect the terminal speed? The surface area. Going back to the skydiving analogy, when you pull a parachute after free fall, the sudden increase in surface area by pulling the parachute increases the air resistance, so you slow down. So let's just take a look at an animation to show what happens. So here we have a skydiver just jumped out of an airplane. They're not actually moving. You can see the velocity is zero. The acceleration is 9.8 meters per second squared. That's the acceleration of gravity. And the weight of the person is 600 newtons. As they start to fall, we can see that they reach terminal speed because the air resistance has gradually increased to match the person's weight. So now the resultant force is zero. We have zero acceleration. So on this diagram here, they're saying that the terminal speed is 50 meters per second. So this is the constant velocity, this is the terminal speed, it's the fastest speed he can reach during free fall. Now we can see what happens when the parachute is pulled. The air resistance increases momentarily and is now greater than the weight, so the object decelerates or slows down. But gradually, as the person slows down, the air resistance reduces because the person is slowing down until the air resistance again is equal to the weight, and the person actually has a new terminal speed, a much slower terminal speed, because their surface area is much bigger. So what else affects terminal speed? Well, the substance through which the object falls. We've been talking about air, but obviously objects can fall through fluids as well. If you drop a marble in a cylinder of oil, and it will reach terminal speed very quickly, and it'll be quite a slow terminal speed. But if you drop it in air, its terminal speed will be much greater. This video shows that the terminal speed does depend on the fluid that the object is falling through. So this video has three balls falling through transparent liquids, but each liquid has a different viscosity, thickness or density. So let's have a look. So we can definitely see that the fluid on the left, the object has the slowest terminal speed, and the fluid on the right, the object has the greatest terminal speed. For whatever reason, it could be the density of the liquid and possibly the viscosity as well. Another one, the shape. The shape of an object affects its terminal speed. Now we've been dealing with coffee filters. Here's a cupcake case, very similar. This is what it looks like from the side, a side view. From below, it really just looks like a circular disc. So here's another shape. Viewed from below, it looks like a circular disc. Will it have the same terminal speed? Well, it looks the same. But let's have a look at a side view. The side view is very different to that of a cupcake case. This looks like a spearhead. And it's not going to have the same terminal speed because of this shape. So the shape of the object is very important. It projects the same area as the coffee filter. So it has a circle facing towards the air. It's the same projected area. But it's much more streamlined, or aerodynamic we might say, if we were talking about cars or aeroplanes. Because of its aerodynamic shape, it's got what we call a much lower drag coefficient, which is very similar to coefficient of friction. And of course gravity will affect terminal speed because it determines the weight of the object. The weight of an object is mass times gravity. So these are the things that affect the terminal speed. Gravity, the shape, the projected area or the surface area, the type of fluid that the object is falling in, and the object's mass. Now let's have a look at an equation combining all those things together. Here it is. Looks very complicated, but let's pick out the different elements. This is the terminal speed, and we're told that it's equal to the square root of 2mg. So we've got the square root of m in there. We knew that from our class experiment. G is gravity. Rho, this is the density of the fluid. So this is a constant relating to the fluid that it's falling in. A is a projected surface area, the circular shape that we were talking about for the coffee filter. And this here, CD, is called the drag coefficient, and this all depends on the shape of the object. So a spear shape or a very pointed shape here would have a very low drag coefficient, whereas the coffee filter itself would have quite a high drag coefficient. So objects can have terminal speeds as well when they're not falling. When an object's falling, we're looking at balancing its weight with the air resistance. Weight is sort of the force propelling it downwards. But if we think of a car or a boat or something like that moving through a fluid, we can see that it is likely to have a terminal speed too when the resistive forces are balanced by the maximum push force from the object, or the thrust force. So let's take a look at the fastest production car at the moment. It's a Bugatti Veyron, top speed 431 kilometers per hour. Why can't it go faster? Let's take a look. There's the car. We have the maximum push from the engine. The car is being driven and the throttle, the accelerator pedal, is flat to the floor. Eventually, as you go faster and faster through the air, the drag force will equal the push force from the engine. When they're equal, the resultant force is zero and we have no more acceleration. The car won't speed up anymore. Terminal speed has been reached. So in summary, when objects are falling through air or any fluid, they reach a terminal speed. This occurs because the object's weight is exactly balanced by friction at that speed. Terminal speed depends on weight, mass and gravity combined, shape, projected area, and the fluid that it's actually falling in. Any object moving through a fluid has a terminal speed, which is reached when the push force is balanced by the friction force.